So now that we have an equation for the average collision rate, how many collisions per second, let's look at what sort of values would we expect for this for, say, a normal situation. So let's assume, atmospheric pressure, and that we just have nitrogen. So what is ZA if we have nitrogen at 1 bar pressure and 298 Kelvin? So room temperature. So first thing we're going to need, of course, is sigma. And again, as I said, that's not something that you can necessarily calculate. It's something you just have to look up. And in table 27.3, you can find the value for nitrogen is 0.450 square nanometers. We can also convert that to meters. Right, so we have 10 to the minus 9th meters, and that's going to be squared. So we end up with 0.450 times 10 to the minus 18 square meters. We're going to want everything in SI units so everything will cancel properly. Okay, so that's sigma. We need rho. Again, that's number of particles per volume. Right, so that's big N over V. And we can use the ideal gas law to get this, all right, because we know the pressure. And we can assume, volume is in that, right? So we can say that little n over V is equal to P over RT. That's just reorganizing the ideal gas law. And then we just want to convert to Avogadro, use Avogadro's number to convert from moles to number of particles. So we need to multiply by Avogadro's number over V. And so we'll have to do that on the other side, P times Avogadro's number over RT. You can look in my notes that I'll post, but I'm going to skip actually writing out all the numbers here. But we have a pressure of 1 bar, we get the right value of R, Avogadro's number you can look up, and then we have T in 298 Kelvin. This will all work out to 2.43 times 10 to the 22 particles per liter. Right, so a little, order of magnitude less than a mole of particles per liter. Now we can convert it. To keep all of our units straight, liters is not too convenient here. We want cubic meters because we express this in meters. Oh, it's hiding behind my face. Right, we express this in meters squared, so we want to keep everything in meters. So we have to remember that 2.43 times 10 to the 22 liters is the same, particles per liter is the same as per cubic decimeter. So then we can say, okay, the definition of a decimeter is there's 10 decimeters per meter. And that's going to be cubed to get that correct. So we'll get 2.43 times 10 to the 25th particles per cubic meter. All right, and then the last thing we need to go into this equation is what is our average speed for our particles. So again, we're using this equation, 8RT over pi times big M. And this is for nitrogen. We know the temperature. We know nitrogen. We can look up its molecular weight. Again, I'm going to skip putting in all the numbers here. They're in the notes that are posted on Moodle for those of you who aren't watching, who are at Connecticut College watching this. And this is equal to 475 meters per second. So if we go ahead and put all those numbers in, we can find the average collision rate. So ZA is equal to 2.43 times 10 to the 25th particles per cubic meter times the collision cross-section of 0.450 times 10 to the minus 18th square meters times the square root of 2 times 475 meters per second. And we can double check things here. We should end up with something that's just a per second, right? How many collisions happening per second? So all of our meters should cancel. So we have meters times meters squared, meters to the minus 3, all those cancel, and we get just per second. So that's why I made sure to convert everything to meters so that everything would cancel here. And we get 7.35 times 10 to the 9th collisions per second. So in our atmosphere, in the gas sort of around us right now, there's about 7 billion, if we look at there's about 7 billion collisions happening every second for, like thinking of a single particle. So that's a lot, but, that there's quite a bit of gas here. And we can think about other sorts of of environments, and they'll have very different collision, average collision. So that is what we've got for our example calculation here.